Hello and welcome to 7.4 of our similar polygon section or chapter. This is section titled Parallel Lines and Proportional Parts. Now, something very, very particular happens with proportional parts. When you have parallel lines, and let's just jump straight into our example. When you have parallel lines, and specifically in specific polygons like triangles, so this is what we call our side splitter theorem. And if I were to draw a triangle, and what if I copied this triangle, pasted it, and these would obviously be congruent. But what if I blew this triangle up and I laid it right on top of the smaller triangle? If you notice, we actually have a set of parallel lines here. These two lines are actually parallel. And if you also notice, let's actually label this. Let's do this in blue. A, B, C, D, and E. Angle A is actually in both triangles. So let's highlight this. Let's highlight this first one in red. And then let's label the big one in blue. And if you notice, A is actually in both of them. Let's do this in purple because that is technically the combination of red and blue is purple, and the angle A is in both of them. And if you know anything, if you remember, when you have parallel lines, we actually have corresponding angles. And that should actually be in two ticks, right? Because they are in the top right. If I drew extensions of this, that is top right corner, in their respective positions, we have corresponding parts. And that actually repeats over here as well. Angle E corresponds to the top left of angle D. So we actually have two similar triangles here. And when this happens, you actually have proportional parts. We know this, that in this particular case, we could state AB will be proportional to AC. Even more so, because if you're looking at it strictly from a triangle part, AB will be proportional to AC. But similarly, we could actually use this. This is not the side splitter, but we could actually say the side splitter is AB is actually proportional to BC. So that's what the side splitter is actually stating, is that, let's fill this in. If a line intersecting two sides, two sides of a triangle is parallel to the third side. So here's the third side that is parallel, ABE and CD. It divides the sides proportionally. And that's exactly what I showed you 2 seconds ago. Proportional. It divides the sides proportionally. So we could actually say AB is proportional to BC. Similarly, we could actually say AE is proportional to ED. Okay? Now just know that BC is not actually the full length of this particular side. It has to be AC. So if we actually wanted to solve for instance, BE to CD, we would have to use different proportions. we'd have to use the entire length of AC properly. So I'll do that in just a second. Yeah, so we could actually say, yep, given, I should have put this earlier, sorry. Given BE is parallel to CD, then this happens. And then, like I said before, you could actually give the entire, length. If you really wanted to, you could use the triangle proportions. And I'm going to put this in pink. Or you could use the triangle, similar triangles. Similar triangles would be AB is proportional to AC. AE is proportional to AD, and then this is the one this is the more important one. BE still has to be proportional to CD. Okay. The reason why I point this one out, I'm going to put a star above this one, is that if you wanted to solve for BE or CD, it's a very specific proportion to these particular sides. Notice that it's not going to be the same proportion. If I gave an example here really, really quickly, if we had, I'm going to erase these just so I could fill them in, and use, let's say, pink 1 to 2, and then 3 to 6. We could clearly see that there is a proportion here. If I fill this in, 1 over 2 is equal to 3 over 6. This second proportion simplifies to 1 over 2, and we see that proportion. But the actual length of the triangle AB of the blue triangle is not 2. It's actually 3. Because AC is really a length of AB and BC. So if we wanted to do this proportion, let's say this had a length of, let's say, 4, right? We wouldn't just straight multiply to 2, or multiply like we did here. 1 times 2, 3 times 6. This would not clean up properly. We would actually need to do the similar triangles here. So be very, very mindful of this, okay? AB is 1, AC is 3, BE is 3, and then we don't know what CD is. Sorry, this is this proportion, but we could solve for it. 3 times 3 is 9, 1 times x is x, and x is equal to 9, meaning CD has a length of 9. So just know that this proportion is not the same. It has to be with these similar triangles. This is why I point this out. So you can still solve for these particular lengths, but you have to use similar triangles, okay? So I personally think this would be worth noting. I put it in pink because you don't necessarily have to know it. Well, let's just say you should write this down. Hopefully you did. No. Hopefully you did. Okay. So with that said, I'm going to erase some of this work just so I could clean this up a little bit. And let's go into our extension. Our extension of the side splitter theorem just states that what if we have, instead of 2 parallel lines, 3 parallel lines? So this is going to be the extension of the side splitter theorem. Of the side splitter theorem. Okay, so this states if 3 or more parallel lines are intersected by 2 transversals, then the parallel lines divide the transversals proportionally. Okay, and let's draw a quick example. Proportionally. Now, when you draw this, I'm going to draw this so that it actually does not make a triangle. And it's important to know that it doesn't have to be a triangle in order to use this theorem. Because if you have 3 parallel lines, you actually have a couple different sections here, right? If I even have a 4th parallel line, if I wanted to, I could say, for instance, say A, B, C, D, E, F, G, H, okay? Then we have proportions that stick out. A becomes proportional with B, AB becomes proportional to BC, along with HG being proportional to GF. Similarly, if you take green, BC is properly proportional to CD alongside GF being proportional to FE. So there's a lot of different proportions that actually happen here. So you could actually say a whole bunch of proportions here. Let's say AB is proportional to BC as HG is proportional to GF. Okay? What it's just saying is that when you have these parallel lines, these transversals become proportional to each other and to the corresponding parts that you want them to. Okay? So, I'm going to put a big or here. You could actually say AB over, and let's use the green this time, CD is proportional to, that's blue again, HG to green, FE. And we could actually see this play out. These blues, AB, HG, are proportional multiple ways. You could actually do a combination of red and green as well. If you really, really wanted to. If you want, you could make these really interesting. BC over CD is proportional to GF over FE. And instead of using blues, we have reds. And if you really, really want to get fancy, you could do a combination of these. You have some proportionalities here too, but we won't go that far into it. Okay, if you wanna dive deep into that, we could. But other than that, this is the extension of the side splitter theorem. It doesn't only require 2 sets of lines. It could be 3 sets of parallel lines or more. Okay, and there is that proportionality that occurs when we have transversals that go through those parallel lines. Okay. If you have any questions, please ask. Bring those questions to class, and I'll see you in the next one. Bye.